Hello guys, welcome on Tesla Eduventures. In this video, we are going to discuss the concept illustration problems based on thermal expansion, and I would try to cover all the small topics of thermal expansion in terms of questions. So let us start with this first question. You can see that at temperature T naught, a pendulum clock has a length of L and this clock is going on accurately at that temperature. Now the coefficient of linear expansion of this pendulum clock is 1.85 into 10 raised to power minus 5, and we have to find out that how much clock will lose or gain the time in 24-hour slot if the temperature of the surroundings is 10 degrees Celsius higher than the initial temperature T naught. So we have already formed a formula that time gain or time lost is equal to alpha delta T divided by 2 into T slot, which we have, this formula we have already discussed. We know that the surrounding temperature is higher than the temperature of this pendulum, initial temperature of the pendulum, and therefore we can say that due to the increase in temperature, the length of the pendulum will increase and the time period of the pendulum will increase. Due to increase in this time period, the pendulum clock will become slow and it will lose some time. Okay, so in this case time will be lost. So lost time will be equal to alpha delta T, where alpha is 1.85 into 10 raised to power minus 5 and delta T is 10 divided by 2 into time period is 24 hours. Okay, so you can see that it would be this is 12 and 1.85 into 12 is 22.2 approximately, and this is 10 raised to power minus 5 minus 4 hours. Okay, so this is the time lost, and if we wish to find out this time lost in seconds, so we know that 1 hour is equal to 3600 seconds. So this would be 22.2 into 10 raised to power minus 4 into 3600. So it would be equal to approximately 8 seconds. Okay, so this is the time lost by the pendulum clock. Now we move on the next question. Now this is question number 2, and this question is based on the effect of temperature on buoyancy. So you can see that there is a piece of metal that floats on mercury, and the coefficient of expansion of this metal and mercury are gamma 1 and gamma 2 respectively. If the temperature of both mercury and metal is increased by delta T, then we have to find out that by what factor the fraction of volume of metal submerged in the mercury changes. First of all, we know that as that metal piece is floating on mercury, so we can say that buoyancy will be balancing mg, and buoyancy will be V immersed into rho of liquid into G, and mg would be V total into rho of solid into G. Cancelling G with G, V immersed upon V is the fraction of volume immersed in the mercury initially, and it is rho S upon rho L. Okay, now at some higher temperature, this fraction will change, obviously, because let's suppose that new fraction is y, where y is vi dash upon v dash, because rho s and rho l will change, and this is, let's suppose, rho s dash and this is rho l dash. Now rho s dash will be rho s 1 minus Now this is solid, so we know that solid has a coefficient of volumetric expansion gamma 1 and divided by rho L 1 minus gamma 2 delta T. Okay, so this is the fraction, and we have to find out the factor by which this fraction changes. So we have to find out y upon x. So y upon x will be equal to 1 minus gamma 1 delta T divided by 1 minus gamma 2 delta T. Now you can further simplify, you can write it down like this, that this is 1 minus gamma 1 delta T into 1 plus gamma 2 delta T. I have used binomial theorem and I have used this power here. This is minus 1. So you can see that y upon x will be equal to 1 plus gamma 2 minus gamma 1 delta T. This is the factor by which this fraction Vi by V will change at the temperature increase of delta T. Now we move on the next question. In this question, as shown in the figure, you can see that this is a pendulum and its axis of rotation is this one, and it is supported by these three rods. This is L1, this is L2, and this is L2. This is an equilateral triangle, and this pendulum is oscillating in such a way such that it is coming out of this plane in each oscillation, like that. So we have to find out the value of L1 upon L2 if this length h of the pendulum always remains constant at all the temperatures, which means that this length is independent of temperature. You can see that if this triangle is this one, then length is h, and if this triangle is this one, then also length is h. Okay, now let us use the formula. Now let us write down the value of h. So h will be equal to under root of L2 square minus L1 square by 4. Okay, this is h, and h will be obviously 1 by 2 of under root of 4 L2 square minus L1 square. Now what we can do, we can square these terms. So this would be 4h square is equal to 4l square minus L1 square. And we can differentiate these terms. So it would be 8h dh, and it would be 8l2 dl2, and this is minus 2l1 dl1. Now dh is 0 because h is not dependent on the temperature. So we can say that 8l2 dl2 is equal to 2l1 dl1. Okay, and hence we can say that 4l2 dl2 is equal to l1 dl1. Now we know that dl2 will be equal to, this is L2, so dl2 will be equal to L2 alpha 2 dt, and dl1 will be equal to L1 alpha 1 dt. So we can substitute these value here. So 4 L2 square alpha 2 dt is equal to L1 square alpha 1 dt. Cancelling this dt with dt, we need to find out the value of L1 by L2. So L1 by L2 whole square will be equal to 4 alpha 2 by alpha 1, and L1 by L2 will be equal to 2 under root of alpha 2 by alpha 1. Okay, so this is the value of L1 by L2 for which this length h of the pendulum remains constant. Now we move on the next question. In this question, you can see that there was a equilateral triangle initially. This triangle is having the sides L and L and L, and this angle is obviously 60 degree initially, and the coefficient of expansion of this side is alpha 1 and this side is alpha 1, while the coefficient of expansion of this side is alpha 2. So we know that due to the expansion at higher temperature, these two sides will finally be equal, but this would be different because its expansion would be different and their expansion would be same. So finally we can draw a diagram that finally this side is, let's suppose, L2 and this is L2 and this is L3, and this angle would be theta. Now let us draw this bisector, and this would be angle bisector as well as the side bisector because this is isosceles triangle. This is, let's suppose, beta. Now you can see that the sine theta by 2 is equal to L3 by 2 L1, in fact L2. This is L3 by 2 divided by L2, and this is cos theta by 2 multiplied by d theta by 2. It would be 1 by 2, and this would be L2 dL3 minus, it would be L3 dL2 divided by L2 square. Cancelling this 2 with 2, so cos theta by 2 d theta is equal to, this is L2 and dL3 can be written as L3 alpha, this is alpha 2, so alpha 2 dt, and minus L3, this is L3 L2 alpha 1 dt divided by L2 square. So this L1, L2, L3 are the initial length, and we know initially L1 was equal to L2 was equal to L3. So we can cancel out this L2, L3 with L2 square, and initially theta was equal to 60, so this would be cos 30. So cos 30 d theta is equal to alpha 2 minus alpha 1 dt, and therefore d theta will be equal to 2 alpha 2 minus alpha 1 dt divided by root 3. This is the required answer of d theta. Now we move on the next question. In this question, you can see that the center of mass of the vessel, there is a vessel whose coefficient of linear expansion is alpha g. It is made up of glass, and a liquid is filled in the vessel whose coefficient of volumetric expansion is gamma naught. Now this liquid and the vessel are heated by a temperature of delta T. So we have to find out the relationship between alpha g and gamma naught if it was found that the center of mass of the system does not move due to the heating. So let us imagine that there is a vessel, and in this vessel there is a liquid filled like that. Okay, and the area of this vessel, area of cross section is A, and let's suppose the initial area is A naught and the height of the liquid in the vessel is H naught. So we can write down that the height of the liquid is volume of the liquid upon the area of the vessel. And we know that if this height remains constant with respect to the container, what I am trying to say is the fact that if there is a scale calibrated in the container, then if the reading of this height remains same, then the center of mass will also remain at its original position. Therefore, this reading of the height of this liquid in the container would be V naught by E naught. Now let us see that at some final temperature, this height again will be equal to original height, because it should remain the same, and it should equal to V by A, where V is the new area and V is the new volume and A is the new area of cross section of vessel. So we know that H naught is V naught by A naught. So V naught by A naught should be equal to V by A. V is the volume of the liquid, so V would be equal to V naught 1 plus gamma, this is gamma naught delta T, and A is the area of cross section of vessel, so it would be equal to A naught 1 plus 2 alpha G delta T. So cancelling this with this, so you can see that 2 alpha G is equal to gamma naught. So if this relation holds true, then the height of center of mass will remain same, and we have to find out the relationship between alpha G and gamma naught if the fraction of volume of the container occupied by the liquid does not change due to heating. So the fraction of volume of the container occupied by the liquid would be, let's suppose initial volume of the liquid is V naught and total volume of container is V. So this fraction of volume is occupied by the container. This is V total. So at some different temperature, let us suppose that this fraction is VO dash upon VT dash, and this fraction VO dash would be VO 1 plus, this is the volume of liquid, so it would be 1 plus gamma naught delta T, and VT is the total volume of the container, it would be VT original 1 plus 3 alpha S delta T, and this fraction should be equal to the initial fraction. So cancelling V naught with V naught, VT with VT, you can see that gamma naught is equal to 3 alpha S. So this is the correct relation for the second part. Now we move on the next question. In this question you can see that there are two metal plates. This is plate A and this is plate B. Okay, so they are made up of same material and they are placed on a frictionless table as shown. So both these plates are heated uniformly, and we have to find out the variation of X and Y with temperature. So you can see that if this is the width, let's suppose this is the width D1 of this plate and this is the width D2 of this plate. So as we can see that D1 is greater than D2, therefore we can say that delta D1 would be greater than delta D2. Therefore this gap will expand more as compared to this gap, so X will increase. And as it is clear that both of these plates will expand, so this length will expand, so this edge will go towards right, and this length would also expand, therefore this edge will go towards left, therefore Y will decrease. So the correct answer is the fact that X will increase and Y will decrease. Now we move on the next question.